So welcome everyone. The topic today is an intuitive introduction to machine learning, or AI as we call it these days. I'll start with the question, what is machine learning and how does it differ from programming? The proliferation of libraries that you see for machine learning or for AI might give you the impression that machine learning or AI is just another discipline of programming. It so happens that actually it couldn't be further from the truth. The approach that machine learning takes to solving a problem and the approach that typical programming takes to solving a problem are poles apart. So I'll start today with an overview of what machine learning is, what its broad areas are, and why is it that it has gained such dominance? Why is it that AI is considered to be the biggest revolution of our lifetime? It is much bigger as a revolution than the internet, than big data, than anything that you can think of, the social media, and so forth. People consider the AI revolution in progress to be comparable in its transformative power towards human society. It is considered comparable to the discovery of fire or the invention of the wheel. Those are considered nowadays the comparable. It is going to turn the world upside down. It has begun to turn the world upside down. The world of today and the world of tomorrow will be unrecognizable to a person who only knew the world 5 years ago. It is that big a change. So the question therefore is, the word machine learning or artificial intelligence, let's take the word artificial intelligence. Let's take the word artificial intelligence. This word is made up of two words, and I'll also put the synonym here, machine learning. Not synonym actually, there are two different meanings actually in the strict sense, but we'll put them side by side. So what is artificial intelligence? The first word, artificial, comes from artifice. To some extent, it's the converse of natural. When we think of natural intelligence, we typically think of biological systems. We consider human beings intelligent. Then we are a little bit more parsimonious when it comes to ascribing intelligence to other animals on the planet. But grudgingly or not, we do ascribe them some level of intelligence. But at some point we draw the line. If I show you a rock, you would probably not be willing to say that the rock is intelligent. So, and therein is the definition of intelligence. Artificial is that which you make. Artifice is the making from our hands, right? With tools. That which you make with hands and tools is artifice. And artificial intelligence is therefore a form of intelligence that you could make with tools. Trouble is, what is intelligence in the strictest sense? It is something that it's a word that we all seem to be very, very familiar with. We think we know what it is. But when it comes to quantifying it, it becomes a little bit harder. To the extent that we are in an engineering and scientific discipline, a STEM field, in science only deals with observables that can be measured, measurable observables. For example, temperature is a measurable, heat, temperature are measurable. Right? Wind speed is measurable. And science only deals with the measurable. But how do you measure intelligence? Today we know that intelligence, all the intelligence tests, so-called IQ tests, are bogus. They are practically silly, to put it frankly. Nevertheless, we do tend to believe that there is such a thing as intelligence. And the question arises, how do you measure it? So we'll come to that. Let's look at the adjacent phrase, machine learning. So what machines are, we know, they are the creations of engineering. But what is learning? And let's park those two things together, because these two words, I suppose, learning and intelligence, they have a deep connection, as we will see shortly. Nevertheless, without being very precise about the definition of artificial intelligence, it has been a millennial dream of almost all civilizations to create artificial intelligence. We have stories. For example, in the East, we have stories of Aladdin and his magic lamp, right? And should you rub the lamp, a jinn comes out. What is the jinn capable of? The jinn, by today's form, you would call, and as the word has become very popular, an AI agent. Ask it to do something, and with superhuman abilities, it will go and do it. And to the extent that there is that legend of Aladdin and his magic lamp, there is a legend of having created artificial intelligence or have a means to conjure up artificial intelligence, an AI agent that will do whatever you ask it to do. In the Hebrew traditions, there is the story of the golem. Apparently, very religious and wise men have the ability to mold clay into a human shape and, in some sense, breathe intelligence into it so that it comes life. And that when it does come alive, it will do what you ask it to do. But beware, it can do also a lot of harm. That resonates with today's concerns. Much as we are aware of the power of artificial intelligence, we are also spooked by the perils that it brings. So the stories about artificial intelligence, the aspiration to create artificial intelligence predates modern technology or the modern industrial and scientific revolution. When Charles Babbage was creating the first computer at a time with gears, his goal, his aspiration was not necessarily just to create a really good, what today you would call a calculator, but his dream of a computer was to conjure up artificial intelligence, a machine that could that could be intelligent. Those dreams are way ahead of their time. Charles Babbage was trying to make his computer with gears. Today we make them with semiconductors. And in the coming days, we'll make them with qubits, quantum bits. So the world has progressed from the mechanical gears to vacuum tubes to semiconductors and imminently, potentially, to quantum processes. Nevertheless, and along with it, artificial intelligence has been making strides forward. Artificial intelligence, so therefore we will talk about it, but more broadly speaking, we can see that it correlates with the evolution of technology, hardware technology. It correlates with the growth of big data. It turns out when we look back at artificial intelligence history, we can see that quite often the mathematics, the algorithms, they predate the technological capabilities to produce intelligence by decades. This year, 2025, there is a lot of buzz about the so-called AI agents and multi-agent systems and agentic reasoning. It seems to be part of the zeitgeist of 2025. Nevertheless, if you look at the history of this AI agents, it goes all the way back to 1980s, 1990s. In fact, much of the theory had been developed already by then. So today what I will do is give you sort of a tourist guide to the whole field. So today's session will be different from the next three sessions. Next three sessions, we are going to cover a whole host of topics, and I will just mention the topics that we'll cover. We'll cover something called regression. We'll cover something called classification. We will cover clustering, dimensionality reduction. Now, these are all esoteric words, but my hope is that by the time we are done, they will all become quite familiar to you. And we will deal with something very magical called reinforcement learning. And it could be safely said that reinforcement learning is having a renaissance. Is literally having a renaissance moment in 2025. Ever since, it has always been there and it has always been marvelous. But in 2025, ever since two big events happened, AlphaFold got the Nobel Prize. The team for AlphaFold got the Nobel Prize, a reinforcement learning trained algorithm. And DeepSeek came out, which showed the remarkable potential of of reinforcement learning, this has become a big topic. So we are going to cover these 5 topics with some little examples and code in the subsequent days, in the next 3 days. But for today, we will stick to getting a sense of what is this field all about that threatens to turn our world upside down. So people, if you look at the history of artificial intelligence, people have tried to quantify intelligence, and they have said intelligence is the ability to think. Stones don't think, but we think, and therefore we are intelligent. But that is arguable because most thoughts are foolish thoughts, or incorrect thoughts. They have error prone and whatnot. So to call a completely bogus argument a remark, a sign of intelligence, is stretching the definition a little bit. And also, thinking leaves no trace. You think a thought, but unless you act upon that thought, it leaves no measurable trace behind. So it is outside the purview of science at this moment. So then how do you deal with the field of artificial intelligence? In science, there is a statement going back to the thermodynamics physicist, Lord Kelvin, who said that you cannot improve what you cannot measure. The more precise statement was that a subject has not risen to the level of science unless it deals with measurable quantities, measurable observables. Otherwise, it's not science. So artificial intelligence, to the extent that it is science and engineering, we need a quantitative definition for it. So here is a definition that I'll give with an example. And so I'll try to, because it's intuitive, I'll try to motivate much of these things with examples and stories. So consider that you take a child to a meadow, and imagine that in the meadow there are cows and there are ducks. And you are in a rather pedagogical mood. You start teaching the child, look at that big animal. Look at the horns and look at that swishy tail and 4 big legs and big body. That's a cow, right? And see how it moves. And then after a little while, you encounter a duck, and then you point your child to the duck and you say, well, look at that small feathery creature, webbed feet, beak, and it can fly, and that's a duck. So you might show a few examples. Now imagine that your child is 2-year-old and is having trouble understanding all the things that you are saying because you are saying too many things. Now, how would you know whether the child has understood what a cow is and what a duck is? Your first instinct could be that you could turn back to a cow that you just showed your child and ask, what is that? Now, if your child says it's a cow, you might feel pleased. If your child says it's a duck, you might safely conclude that your child hasn't understood. Child is just guessing. You show a few examples and you get the answers. Now what happens is that, how do you know that the child is learning the concept of a cow or the concept of a duck? What is that essence of a cow, the cowness of a cow, that makes an animal to be called a cow? What is that essence of a duck that makes you call an animal a duck? The child has to grasp that. So observably, in a quantifiable way, what you could do is show lots of examples of cows and ducks and ask the child each time, what is it? And you could keep a track of the error rate. Now, you would know what the error rate would be if the child had no clue. The child would be wrong half the time. Whatever animal it said, it would just guess and throw out a word, cow or duck. That is a baseline error rate. It is getting it wrong. But let us say that after a little while you observe that the error rate is lower than the baseline. In other words, let's say that instead of being wrong 50% of the time, your child is wrong only 20% of the time. what would that indicate to you? It could potentially indicate that the child is beginning to grasp the concept of a cow or a duck. So that brings up the concept of our error rate, which is foundational to learning. Error rate, right? Or errors. What you do is you just keep track of the errors, the number of errors. The more the errors, more error means not yet learn, right? Less error means not yet. As you see a decrease in error, you can conclude that the child is learning. Would you agree with that? There is a subtlety here. You don't want to show the child the same cows and ducks that you identified and explained. Child might have a photographic memory and may have just memorized, and all it may remember is all this, and this animal happened to be called cow without understanding what a cow is. So what you want to do is show other examples. Take the child to other parts of the meadow and ask, what are those animals? Are we together? But leaving that aside, leaving the corner case of memorization aside, we'll keep it simple. We'll say that if the error rate goes down, child is learning. And therefore, learning is quantifiable. The statement I'm coming to is that learning is quantifiable through measuring errors. And as you see a gradual decrease in errors in the prediction, in the identification, you can say that the child is now learning what a cow is and what is a duck. And so that is the definition. That is, then comes a very interesting thing. Instead of a child, instead of your biological entity, what if a machine could exhibit a similar behavior? What if a machine somehow, so imagine in the very simple sense that you're sitting in front of a machine and you're talking to it. Now that might look rather quirky, but let's say that happen chance, you're talking to the machine and the machine is continuously looking at pictures of cows and ducks. And every time it sees a picture, it either points to the word cow or points to the word duck, emits the word cow or emits the word duck. If it is just a dumb machine, it would be randomly doing that. On the other hand, if you notice that as you keep talking to the machine, after some time, the error rate in the machine goes down. Should that happen, you would be left with no other conclusion but to say that the machine itself is learning. Because when you say that learning is quantified through measuring error rate reduction, that's the important word, reduction. Then, if machines can exhibit, they too can learn. One of the most amazing discoveries in the whole field of science has been the discovery that machines too can learn. It is one of the most amazing facts. So it turns out that intelligence is not necessarily the prerogative of biological systems. Learning is not the prerogative of just biological systems. Machines can learn. And if you just pause and think about the sheer implication of it, it means that intelligence, therefore, can be produced in the laboratory, in machines. We can say that a machine exhibits intelligence if it has a capacity to learn. And the same is true for biological system. Anything that has a capacity to learn has intelligence. And it is artificial intelligence if it is a machine, if it is an artifice. And that's the word artificial intelligence. It's sort of the artificial intelligence, though, strictly, is a big topic which contains robotics and many things. But its core, theoretical core, the foundation is machine learning. So if this is AI, this is machine learning. Because it is the learning in machines that produces intelligence. Are we together, guys? This field of artificial intelligence has a long history, and based on who you talk to, you will get many different narratives. People often refer to McCarthy and a mathematician and scientist McCarthy in US, who was instrumental in the creation of first sort of a summer school and who coined the term artificial intelligence in the 1950s. Nevertheless, this field predates McCarthy by over 100 years. The first measurement of errors and a systematic way to reduce errors and therefore to teach a machine was actually done by a person whose paper on this dates back to 1793. And I will keep the surprise of who that name is, and I'll let you for a moment guess the name of this person, but I will tell you his story. He was the son of a coal miner whose father believed that life is hard, and he wanted to teach his son practical aspects of coal mining. The child, on the other hand, was a bit of an academic bent of mind, and he liked numbers, and he had a facility with numbers, which was noticed by his school teacher who sort of supported him. He grew up to be one of the giants in physics and mathematics. It is said that when he was given a problem by his schoolmate in a chemical reaction, rate of chemical reaction, and to solve it. And while he was trying to solve it, as a byproduct, he invented what today we call, it has a very interesting name. It's called the method of least squares. Method of least squares. He kept that to himself broadly. Then there was in Europe, there used to be a tradition that they would throw grand challenges. Just like your Kegel competition, there used to be grand challenges. And one of the challenges was that there was a heavenly body, a planetoid, I believe, that was Ceres, I believe, that was supposed to show up in the sky. It had gone behind the sun, and it would take quite some time to show up, come back, and be visible from the Earth. The grand challenge was, who could predict when will it show up again in the sky, and where will it show up? So you realize that the problem was interesting. You had to predict the time, and you had to predict the location in the sky where it would show up. Now, location is hard enough. If you ever lie down on the ground and look at the night sky, sky is vast, and anywhere it could show up. And then on top of that, you had to predict the year, the month, the day, the time that it would show up. A grand challenge. Many people submitted their predictions, many mathematicians and astronomers. They put in their guess, and physicists put in their guess. And they were all wildly wrong, except for the guess, in quotes, the calculation of this one mathematician, physicist, who got it with uncanny accuracy correct. The rumor has it, and I don't know how historically accurate it is, that to coax Gauss to reveal his secret of how he did it, those were the days when they were still coming out of the dark ages. Rumor has it that they threatened him that we'll accuse you of witchcraft unless you tell. It's too good an estimate. And so then he came and wrote a paper in 1793. And there also he was rather coy. He didn't quite reveal the secret. Then in 1805, another great mathematician, sorry, the name of this mathematician, I think you guys must have guessed. I blurted it out a little while ago. Anyone would like to say that? His name was Carl Friedrich Gauss. He's considered one of the greatest mathematicians and often called the Prince of Mathematics. His paper was 1793. Then in 1805, Legendre wrote a paper literally by this name, and then Gauss came forward and said, no, wait a minute, I discovered this first. And that led to a debate that raged for 200 years till it was finally resolved by Stigler and shown that they had both independently discovered it. What Gauss had done is he had come upon the same argument that we did, quantify the error and have a systematic way to reduce the error. The systematic way to reduce the error is synonymous with systematic way to learn. So that was machine learning, and that is the long, long history of this field. It started from then. Over the years, it has matured and blossomed and become a vast field. It is so vast that nobody today can claim to know all of AI. No one can claim to know all of AI. It is truly a vast field. I have been studying it now for decades, what used to be called machine learning. And I think I'm just barely scratching the surface after all of these years. So this is the beautiful field of artificial intelligence. What does it achieve? We'll talk about what it can achieve. And I will do it and distinguish it from problems that programming cannot solve. So I think when we think of what cannot be programmed, people often think of, for example, chess. Can you program a machine to win at chess? The reason it doesn't work is that as the number of chess moves possible from any starting point is like you start with the board, you go 3 steps forward, and the number of possible moves and combinations just combinatorially explode. There are more moves possible than there are atoms in the universe. You cannot possibly do an exhaustive search of all those moves and determine which is the best move to take at any given point. There is no computer big enough in the world that can do an exhaustive programmatic search, enumerative search through all the possibilities and quantify what is the best move. Are we together? So in other words, the search space is practically infinite. Rule-based systems, code is rule-based. Heuristics, some specific heuristics, some rules you encode, and they are not able to do. But what can you do? You can set a goal. What is the goal in chess? Well, the goal is very simple. It's to win. If you give it a goal, then you can train a machine through a process of what is called reinforcement learning. A beautiful idea. And the machine will make lots and lots of mistakes. In the beginning, it will play like a fool and make the most obvious mistakes and lose. But machines have infinite patience. And it can go on playing with itself billions and billions of times. And eventually, it will learn to play in a way that will beat the grandmasters. And it did beat the grandmasters. Today, nobody in the world can claim that they can beat a computer, an artificial intelligence at chess, or at the game of Go. So how did the machine learn it? In this particular example, this example of reinforcement learning, which by the way is a very, very hot topic these days, as I said, the process is, and I'll give you an example of how this works. The way it works is this. Imagine that you take your same child to learn tennis. You go to a tennis court. There are 2 ways of teaching your child. One is you teach your child, hold the racket this way. These are the rules of the game. This is how you hit the ball. What are you doing? You're programming your child in some sense. Do this. If this happens, do this. If that happens, do this. After a little while, you'll realize that even in a simple game like tennis, there are far too many combinations. And it's hard. Easy to teach the rule and say, always run to the ball and hit it and put it on the other side of the fence. But that's usually not enough to teach a child how to play tennis well. Right? It does help, and most parents do that. But here is a different way of teaching your child how to play tennis. You take your child to the tennis court and you say, here's the tennis racket, there's the ball, there's an opponent, go play. And if the child says, how in the world do I play? You say, just try it out. But how, then she would ask, but how would I know that I'm playing correctly? Then you say, all right, I'll do one thing. I'll sit on the sidelines. Every time you do something good, every time you act, do anything on the tennis court, I'll give you a reward. And the degree of reward that I give you will be proportionate to how good a move you made, how good your action was on the tennis court. Are we together? Right? So the child may go from action 1 to action 1, action 2, action 3. Each of these will have a reward, and the ultimate reward is to win the game. So what you have done is you have associated an action. So the child hits the ball off the court, you give a thumbs down. The child hits the ball to the other side, to the opponent, makes the opponent run around, and you give a thumbs up. Right? And so what will happen is, in the course of time, this child will learn to play. Now, the remarkable thing of teaching a child how to play like this is, you did not make it rule-based. See, when you make things rule-based, when you do it with your own child, there is a limiting factor, there's a ceiling. Your child only learns your rules, so your child can play only as well as you can play. Which means that you not only propagate one generation forward, the ability to play, but you also propagate, unfortunately, the ability to play as badly as you play. Right? That is the ceiling. On the other hand, when you leave a child to just figure out her own style of playing tennis and just give indications through rewards, it opens up enormous possibility that the child may outdo you easily in due course of time. And that is what we observe in machines. And that is one of the most beautiful things that we find about artificial intelligence. We find that for specific tasks, almost always the machines that we train, they far outdo us. Today, we marvel at the power of these chatbots, the ChatGPT and Anthropic and Cloud and Gemini and DeepSeek and Llama and so on and so forth, all these chatting large language models. And if you observe carefully, they seem to be far more knowledgeable than we'll ever be. And they have begun to reason. Sometimes they reason in a very flawed way. But if you narrow the domain and you specialize, train it, fine-tune it for specific domains, invariably, these machines beat us hands down. And that is the great promise of artificial intelligence, that we may just be the parent teaching these machines with the hope that, like our own children, they will far outdo us in the coming days. Therein is also the peril. You don't expect your child to turn around and kill you after some time, but there is a genuine fear among people that this artificial intelligence, when it develops a form of intelligence, a level of intelligence that is far, far more than what human beings can understand, will it consider that the best way to save the planet, perhaps, is to get rid of this troublesome humans who are making a mess of the earth? For example, it could easily be possible, and therein is the peril of artificial intelligence. And those are real questions that go to the ethics and to the questions of responsible AI. So far, we try our best to train AI to be what we call helpful, harmless, right? And all the other good qualities. Right? And they are by and large that, though people have a sneaky feeling that we don't know if they really are that or they are just behaving like that while we are observing them. Right? Very much like naughty kids. So that remains an issue with intelligence. Now, take this example of teaching artificial intelligence to beat us at the game of Go. DeepMind, the research team that created that, had a remarkable thought after that. They said that if we could train it, could it solve a problem that is supposed to be a millennial problem in biology? In biology, with proteins are what are called macromolecules. They have hundreds of thousands of atoms in them. They're not like water, which has 3 atoms. They're huge. They're made up of amino acids. And amino acids themselves are complex molecules. Right? So The question is, what is the structure of that molecule? How does it look in three-dimensional space? The reason you would, for practical reasons, want to know the structure of a protein is because the protein is a long chain, and as it folds onto itself, some parts of the protein are exposed and some parts are not. And it is the exposed parts that are the active parts that you can attach to, you can interact with in a protein. So knowing the 3D structure of protein is foundational to being able to do drug discovery and looking for cure to diseases. Scientists used to take, a team of scientists would take a couple of years in a laboratory, and if they were lucky, they would guess the structure of a protein to reasonably high accuracy, let's say 85–90% accuracy. There would still be some errors, but they would know the 3D structure of a protein. People literally got Nobel Prizes at some point for discovering the structure of some proteins. It was a hard journey. The human body has a lot of proteins. Planet Earth has a lot of proteins. And yet, it was foundational to such practical concerns as diseases and drug discovery. AlphaFold team thought, could this problem be solved? Now think about it. You have a long chain molecule that could fold itself in any which way. There are all these forces of valence bonds and attractions between atoms and so on and so forth. So they applied AlphaGo algorithm adaptation and called it AlphaFold, the protein folding problem. By the time, and right away, something that was supposed to be a millennial problem, it managed to solve just like that. In one stroke, it found the geometric structure of all the proteins in the human body with very high accuracy. Not zero error rate, but very high accuracies, equivalent to or surpassing that what people were doing in the laboratory through actual test tubes and chemicals and reagents. Remarkable discovery, because you don't have to wait 100 years to know the structure of all the proteins and therefore to do drug discovery. Right? A pretty big deal. And after that, of course, as many of you who are keeping track of it know, the pharmaceutical industry, the drug discovery and disease thing, research papers are coming out now at a breathtaking pace, discoveries after discoveries. One physician here, who's part of a team, once told me a surprising fact that I still am wrapping my head around. He said that in the field of medicine, more knowledge is being produced every 6 months than has been produced in the entire history of the medical field. So think about it this way. Discoveries are happening now at such a breathtaking pace that more is done in 6 months than has ever been done before. It's an astonishing fact. And it is no wonder that this team, for this AI team, which probably has never held a test tube or done a biological, northern blot or southern blot or any of those reactions, was given in 2024 the Nobel Prize in Biology, in medicine. An absolutely remarkable discovery. And the story goes on, actually. A British group, researcher, a very elite researcher, I forget whether it was Oxford or Cambridge, had discovered a molecule in the context of some disease after close to 10 or 12 years of research, a team. And they were approached by DeepMind and said that, see, we need a hard problem to solve. And then those researchers said that, no, look, there is no way AI could find this answer on the web because we haven't published it. But we can articulate the problem and let's see what these machines can do. And so they articulated the research problem. And the group, then the machines, all that big AI supercluster went humming along. And I believe in about 24 hours, and I might have some of the details slightly off, but it came up with 3 molecules as a potential solution to the problem. To everybody's astonishment, one of the molecules was what they had discovered after 12 years or so of research. So the world is being turned completely upside down at this moment as we speak. given the way artificial intelligence is galloping ahead. And we all see it. Today, most of you cannot do without Google search, which is AI driven. You cannot do without, I don't know, one of the chatbots, ChatGPT, Cloud, Gemini, etc. You engage with it on a daily basis. You talk to Siri, or to some voice activated thing, which does speech to text. Now there are agents that do text to speech that imitate your voice. The world is more and more about AI. You go shopping, it makes recommendations. Those recommendations are being produced by AI. Today, the statistics is more things are bought that AI recommends on an e-commerce portal than bought through primary motivation, namely you realize that you're out of something, you're out of coffee mugs, and you go to the website to look up coffee mugs and buy it. So that is a primary motivation to purchase something. You know what you want to buy and you search for it. Actually, most things are bought because the AI recommends those things to you. So AI is all over our life these days. Now, with that introduction, we can ask, what are the broad areas of AI? Right? And I will go over those broad areas one by one. I will say that the first thing is basic statistics, which you should not ignore. We should do that. We must know that, I will call it descriptive statistics. Then you have one thing, something called supervised learning. Then you have something called unsupervised learning. And then there is something called reinforcement. Within supervised learning, the better term that I like is to call predictive model because it's more easy to understand. Basically, you give it an input, it produces a prediction. That's what supervised learning or predictive modeling is. Unsupervised learning is the better term, a more descriptive term is pattern recognition. You recognize a pattern in the data. And reinforcement learning, we just went through an example of that, a child learning to play through just hints about how well she's doing without being told the rules. Predictive modeling has further branches, and then there are sort of other branches, but you basically talk about classification. For example, teaching a child to tell whether an animal is a cow or a duck is classification. There are one of two possible answers. Then the other is something called regression. And we will deal with these in the coming days in great detail and with code and with examples. But regression is when the model predicts a number. So for example, if I can tell what will be the weather at 7 p.m. tomorrow evening, what will be the temperature? The temperature is a number, isn't it? Or I could say what will be the temperature, pressure, wind speed. Then it's an array of numbers, a vector of numbers. Whenever you predict numbers, it is called regression. Whenever you identify or predict, whenever you predict whether something, identify, a machine says, this is likely to be a cow, or this is likely to be a duck. Or more realistically, whether or not, let's say, a credit card transaction is fraudulent in more practical terms. Your answer is binary. Or if I say, you're looking at a car, which of these 5 models it is likely to be? That is identification. That's predicting a label. It's a sports car, it's a convertible, it's a SUV, it's a truck, or something like that, right? So those are a sedan. Those are identifications or prediction of a type. Whenever you predict a type, it's classification. Likewise, for unsupervised learning, you have a dichotomy. You have clustering, and you have something called dimensionality reduction. Very briefly, clustering is suppose you look at data and your eyes can immediately notice that some points are clustered together. For example, when you go to a social gathering, have you noticed that as more and more people join a social gathering, people tend to form small clusters and they sit in clusters and talk to each other. And discovering those clusters is called clustering. Dimensionality reduction is another form of pattern. If you notice that even though people could be anywhere on a playground, but for whatever reason, all the children are standing in a circle. Maybe they're playing some game which requires them to be standing in a circle. So then what happens? If you consider each child as a data point, they all exist on a circle. A circle is one dimensional. It's a curve and it's occupying less space than the whole playground. A playground is two dimensional. So that is called dimensionality reduction, recognizing that data actually lives in lower dimension than you thought. And then reinforcement learning, we already gave an example. So today, what I will do is I'll start with perhaps the humblest of them all, descriptive statistics. And it is quite often overlooked in these days of rush. Today, if you talk of AI, people immediately start talking about AI agents, large language models. You look at the news, and even popular media is filled with these big words. And everybody wants to start by learning there. It's like everybody wants to start learning a subject by first picking up a PhD thesis and then saying we'll do the kindergarten stuff later. It doesn't quite work that way. So let's not put the carriage before the horse, but start in a more historically or a chronological fashion, the way things evolved. So today I'm going to talk about descriptive statistics. What is statistic? This itself, the word requires some attention. So now we're going to talk about the easiest of all things, what I call descriptive stats and data visualization. People often call it EDA, exploratory data analysis. So I'll start with descriptive statistics first. Descriptive statistics. What is statistics? Statistics seems to be the plural of the word statistic. What possibly is a descriptive statistic? Here is one way to think about it. Suppose you have a population. Let's say you have a population of human beings, population of children in school. And I ask you, what is the average height and weight of those children? Two different numbers. But let's just take height. What's the average height of children? Now you're asking for a quantity that is not attributable to any one child, but it is something that every child contributes to the construction of. You cannot take the average unless you have measured every child. So it is a number that somehow speaks to the whole and is derived from the whole population. Anything that speaks to the whole and is derived from the whole population is, in a sense, is called a descriptive statistic. So average height is a descriptive statistic. Likewise is average weight. Likewise is minimum height, because you wouldn't know the minimum height till you have known the height of all the children. Likewise, the maximum height or the median height, you see that, right? Or the standard deviation of heights, the variance of heights. All of these are, each of these is a statistic. In some way, they tell you something about the population. When you come to know, let us say that there are a bunch of people, and you come to know that the minimum height is 6 feet 2 for a group of people. It tells you something about that population because that comes as a surprise. You would be inclined to believe that there must be a team of basketball players, isn't it? On the other hand, if I tell you that the maximum height of a group of people is 4 feet, well, that itself would come as a surprise, and you would be inclined to believe that you're looking at kindergartners. You see that, right? So every statistic speaks to something. If I were to tell you that in this group, in this population, the spread of height is only 4 inches, but in another group, the spread of height is 2 feet, you might be tempted to deduce that the first population refers to one particular class, where a class of kids, grade of kids, whereas the second population probably refers to the whole school, isn't it? So descriptive statistic in some way gives you an inkling about the population. And to really understand the population, you need more than one statistic. So we talk about the different statistics: min, max, average, geometric mean, harmonic mean, and these are words that you have learned at some point. Harmonic mean, standard deviation variance, then skew, kurtosis, and so forth. Right? So let us say if you are familiar with these terms. Min, we are all familiar with, I hope. Maximum is the biggest of them. Average, we all know what it means. Geometric mean is the, suppose you have numbers x1 to xn, you take the nth root of the product, right? Then harmonic mean is the mean of the reciprocals, derived from the reciprocals. Standard deviation and variance, we know what they are. We have learned in school. Skew, perhaps you may not have. So I'll just give you a sense of what skew is. Suppose you get the data and you draw the histogram, the frequency plot of the data, and then the plot. So what you do is you imagine that the contour of the plot is the head of a duck. Now, which way is the duck looking at this moment? If you think that the histogram, the frequency plot, is the head of a duck, the tippy tips, the contour of the head of a duck, you would agree that the beak is pointing to the right. So you would say this data is right skewed. Right skewed. On the other hand, if you notice that another data is like this, right? The frequency plot, when you do this, it is like this. So that now you can say that I can see my duck seems to be looking to the left, isn't it? So you call this left skewed. Left skewed. That's what skew means. But what if the duck is looking straight at you? Like this, right? This is your, it's looking neither left nor right, but looking straight at you. So you call it unskewed or symmetric. Symmetric, right? Or skew is 0. There is no skew. Now, that is skew. So now we know what skew is. What in the world is kurtosis? Kurtosis is actually one of the big things that makes e-commerce possible, actually, this word. Kurtosis is how long and heavy the tail is. So this beak, how much mass there is in the beak. So if you weigh the duck, you can ask how much of the weight of the duck's head, is in the beak versus the remainder. Now you can have your definition of the beak. You usually don't use the word beak, use the word tail. This is the tail of the distribution. People use fancy words, the tail of the frequency plot. Right? So how heavy is the tail? And another way of thinking of it is, if you think of it as a beak, how big and long and heavy is the beak? So that is a measure of kurtosis. Kurtosis, it turns out, is a very, very important statistic that you would like to measure in a population. Because think about it this way. There are, if you look at books, for example, or things, you notice that if you go to a small bookstore, it will have, let's say, capacity for 1,000 books, right? your neighborhood bookstore. 1,000 different books it can have. Common sense says that the bookstore owner, the business owner of the bookstore, should go and stock the top 1,000 bestsellers, isn't it? Can pick maybe 10 subjects or 100 subjects or 50 subjects, and in each subject stock the bestsellers that is most likely to sell. Yet there are many books or many movies or many things that actually have very small audiences, that they are not bestsellers, but they sell still in small quantities, right? For example, I like the science fiction author Ursula Le Guin. She's written marvelous stories, or I consider them marvelous stories if anybody knows Ursula Le Guin. She was never a bestseller. I believe she wrote her stories in the 1960s. She's still going strong. Every year there's some book sale of her books. Right? So what happens is that there are lots and lots of things which have small audiences, small markets. Nevertheless, they are popular. Take even the best textbook written by a Nobel laureate, let's say in physics. You go and get Richard P. Feynman's lectures. Nevertheless, it is not a bestseller by any measure. It is a book that continually sells, isn't it? If you take even such things as Shakespeare, any of the Shakespeare's plays or sonnets, collection of sonnets, are never the bestsellers in modern day. Nevertheless, they have a perennial sale. They are the great classics. So what happens is, if you do a frequency plot of items, you will find that some items have excessively high, they are the best sellers. But then there is huge tail, long tail, and a heavy tail of items. There's so many items that some item Xi that sells. So let's say that A, B, small quantities sale. And in fact, the reason e-commerce beats brick and mortar store is precisely because of that. Because if brick and mortar store can only stock this, but an e-commerce store can stock the long tail. Because it can stock the long tail, the cumulative weight, the mass that is here, far exceeds the mass in the head, because this tail just goes on and on and on, right? So the total volume of things sold, or the total revenue generated from the long tail, is vastly more than the sale from the bestsellers. And therefore, the business proposition of e-commerce, right? It is literally because the sales volume of things shows a distribution that is right skewed and heavy tailed, isn't it? Most of the mass is in the long, long, long tail. That's where the revenue is. So that is called kurtosis. So these are single numbers about a population, people. It is also called single, in more formal language, single variable statistic. These quantities, single variable statistics, or univariate statistics, more formally univariate statistics, because it's about height, or it's about revenue, it's about sale volume, number of sales, or things like that. One quantity that you associate with each member of the population. On the other hand, you could ask for a relationship between two statistics, or two things, two numbers. For example, again, go back to the children, a population of children, right? Oh, before I go to two variable statistic, I want to introduce one more concept, biased versus unbiased. Have we ever encountered this word in literature where people say this is a biased statistic versus unbiased statistic? Now, the colloquial meaning of biased is you just say that your data that you took was bad, right? So if I want to prove that most people don't like, in some country, the current, the leader, prime minister, president, premier, whatever it is, an easy way to do that is to pick up a population of the disgruntled ones and ask for their opinion, poll their opinion, and then come to the conclusion that the vast majority of people polled, right, don't like the current leader and therefore is unpopular. So that is bias, that's deliberate bias. But when mathematicians use the word a bias statistic, they actually mean something quite differently. See, sometimes it's not feasible to measure a quantity across the entire population. For example, if I were to tell you what is the average weight of human beings? Oh, good grief. Can you line up 7.5 billion human beings and measure them and find the height? You cannot, right? It's not feasible. So therefore the question arises, can you nevertheless still have a good estimate of the height of human beings? Imagine you're an alien who has just landed and you want to get a sense how tall are human beings in general. What would you like to do? You would like to take a sample, not the population, but you would take a random sample. You would take a random sample, and because you took a random sample, you can now measure from the random sample. You say this random sample is representative of the population, isn't it? And if the law of large numbers hold, so long as your sample is big enough, people often use the square root rule. Take the square root of the population and then go sample. So let's say the population of human being is, let's just say 8 billion, right? 10 to the 9, isn't it? So that is 80 into 10 to the 8. And so you could say that to the first approximation, its square root is, what is it? 9 into 10 to the 4, 90,000. So people often say that if you just go measure the height of 90,000 people, you have a pretty good chance of getting it right. There's another way. You can take lots of samples and we'll come to one of the most beautiful results. But even 90,000 is rather infeasible, isn't it? But let's say that you have a sample, small sample. And we will try our best. We will claim that the sample has been done honestly. Means you have truly made effort to pick a random sample of people and of a sufficiently good size. Let's take a sufficiently good size, right? And you may not go all the way to square root of p, but you may go and pick 100 people or 10 people or something like that, random people, and take their height. The smaller the sample you take, the more likely you are to be wrong, isn't it, guys? That's common sense, isn't it? For example, if you take a sample of 1 and you call whatever this guy's height is, that's a measure of what the average height of the population is, you're most likely to be wrong, right? But nevertheless, suppose you take the sample, then what will happen is the average height, there is a beautiful result in statistics, and one of its crown jewels. This is why sampling actually works at all in practical real life. It is called the center limit theorem. Actually, this theorem has many variations, subtleties. So I will call it center limit theorems. Broadly speaking, what it says is that suppose you take the average, you take a sample S1, sample 1, and you find the average, right? Average is usually given as mu1, let's say, right? Mu is a Greek symbol. One of the traditions in this space is that when you talk of some computed variable, people often use Greek letters in this space. So, and then people use different conventions, but I'll just oversimplify. Sample 2 will lead to mu2, sample 3 will lead to mu3. And so you take lots and lots and lots of samples, right? Let's say 10,000 samples. So you will have big, so let me just say n is equal to 10,000. You end up with lots and lots of averages. Now you would agree that each of these averages won't exactly match, isn't it? Especially if your sample size is small. Does that make sense, guys? Like, I may choose a sample size of 15. 15 human beings average is very unlikely to be the true average of the population. There would be subtle biases in there. And so you take lots and lots of average every time making an effort to be random. You end up with a lot of average. Now there is a beautiful result that says that if you plot the averages, you make a histogram of the averages, a frequency, let me just make it a frequency plot. A frequency plot is called a histogram. It's just a histo is Greek, but common word is a frequency plot. If you make a frequency plot of these mu's, these are the mu values. What you will notice is that these mu values will form a bell curve. Remarkably, they will show a bell curve distribution. So this is a statistic, right? The values, the averages, will show a bell curve distribution. Are we together? And the amazing thing is, the center limit theorem says that the center of the bell curve, this will actually match more or less the bell curve, the mean of the population. Even though you never measured the population, you would get a fair estimate of the mean height of human beings, average height of human beings, by just taking a lot of these samples and putting it together. Isn't that one of the most remarkable results? So it is true whether or not the population itself, even if, let's say that you have height, for whatever reason, let's say that the height of human beings has a distribution. Actually, height of human beings does show more or less a bell curve like distribution. So let me take another thing. Let me take the wealth of human beings. So the wealth of human beings in any country would show a distribution like that. The genuine wealth. Now, this is the ground truth. But suppose you do a poll and you try to find out what is the median wealth, right? What's the average wealth of people? What you can do is, even though the underlying distribution is skewed, you can find the median wealth, average wealth of people. And when you plot it, the average of the averages will hit upon, no matter what the distribution is, it will hit upon, let's say that, for exaggeration, I'll just taper it off, right? Even though it is like this, it will hit upon the population average. Isn't that amazing? Right? That is one of the most magical results in statistics. It's called the center limit theorem. And in fact, that is what makes a lot of statistics and machine learning and AI possible at all. Because nobody ever has access to all the data. We always have access to a sample of the data. We train machines on samples of the reality, not all that. You take your child and you show your child some cows and some ducks. You cannot possibly teach your child by showing your child every single cow and duck in the universe, right? So that's the nature of this. So because of the center limit theorem, you can find the value. But there is a sort of a fly in the ointment here. And the fly in the ointment is a statistic whose average whose average points to the population value is called an unbiased statistic. It is truly unbiased. And by the way, I'm being sloppy here. So for those of you who are statistical majors here, you may say, wait a minute. I'm deliberately being sloppy because I want to convey the big ideas. On the other hand, there are certain statistics that are not actually true. They will give you an incorrect view of the population. So for example, I'll give you an example. Suppose you take sample of people and you see what is the variance of their height. So suppose the population, the height goes from, this is the min, this is the global min, and this is the global max, right? Any sample of people that you pick will have a height distribution. You'll pick some people. It's very unlikely that in your little population, the smallest guy in the world is included. It's also very unlikely that the largest guy in the world is included. Let's say that you're in a school, your population will vary like this. You happen to be in a basketball court, it's like this, right? You happen to be somewhere, it's like this, it's like this, like this. So what are you noticing? Variance or standard deviation, let me just call it variance. For each of these numbers, you can keep on taking samples and finding their variance. But do you think that the average of those variances is the same as the global variance? No, the global variance is this much. This is the population variance, right? The spread of the population. Any sample you take, intuitively you can see will not contain the min and the max and the outliers. Therefore, its variance will be low. And so you may go on averaging all those variances and plotting the histogram. You will always underestimate the true variance of the population from the sample. You won't get it. So you say that this sort of statistics is a variance, is a biased statistic. Because that which you derive from a sample does not hold true for the population, isn't it? It's a cautionary tale. There is actually variance, turns out that you just need a little bit of correction. So typically variance is, the formula for it is xi minus mu square, right? Sigma square. Typically when you do it, you're taught like this in school, high school, isn't it? Count the number of points, find the deviation from the mean, and then average it, right? Average squared this thing. But actually, to fix it, all you have to do is, to make it unbiased, people figured out that all you have to do is a crucial -1 in the denominator. So you will notice that machine learning and AI books, they put and it looks rather puzzling, that when they write the variance, they always put an n-1 in the denominator, not n. And you say, wait a minute, didn't I learn it differently in my high school books? And the reason for that is high school books at that moment simplified it. They're looking at the whole population. But when you're trying to guess something about the population from the sample, then this -1 correction does the trick. It is just about a little bit, because if you make the denominator a little bit smaller, what will happen to the quantity? It will become bigger. And that is what you do. It's a way to stretch out this from the variance of a sample to guess the variance of the population. So that's that makes it sort of, it's a way of making it unbiased, make it unbiased. -1. -1, right? And it's mathematically justified. So that is that. But now let's come to a little bit more interesting fact. Let's come to something that people keep talking about very popularly, called correlation. I'll talk about correlation, covariance, and sequentiality. These three things are related. First, I'll talk about one of the fallacies that one of the great data scientists, Stigler, wrote a lot about. It's one of the common fallacies that happens, and it happens in every country, in every place. See, in any organization, whether it's a country or it's your workplace, whenever there is a change of guard and a new boss comes, in a company, it will be a new director, new manager coming in, new VP coming in. In a country, it will be the new president, the new prime minister, the new premier coming in, right? So what happens is that a common observance is that right after the person's coming, when good things happen, the person says, see, I came and it worked. Things are working now. There's a converse of it also. Then you say, well, if that is true, what about that disaster? Right? Then they say, that guy before me, right? He left a mess that I'm still fixing. Right? And you see it everywhere, whether it's an organization, it's a country. Right? Every leader blames the predecessor for the mistakes and makes claim for all the successes. Right? And it goes not just with leaders. People, you have a garden, you have you water the garden. When roses bloom and flowers bloom, we all take the credit. See, because I've been watering it for the last so many days, therefore there's flowers. But if all the flowers wilt, oh God, it's because of weather and God and fate. So now I'm going to speak to that. Unfortunately, and this is how AI, actually the reason I'm giving this cautionary tales is I always feel that learning of AI should start with these cautionary tales, because in a rush we forget these stories. I'll tell you a story. I came to Silicon Valley in the 90s. Right after that, Silicon Valley became Silicon Valley. There was a dot-com boom, great things happened. Therefore, it all happened after I came here. Therefore, I must be responsible for it, right? I must get the credit for doing that. Well, of course, you can point out that I must then be responsible for the bust also. So, believe it or not, this idiotic way of reasoning is far more prevalent than we think or we are willing to accept. It's one of the most common fallacies of human beings, temporal sequentiality. So, I can best illustrate it with a story. At one time, and by the way, this is Berkeley. You see, Berkeley is world, at least in US, number one in mathematics, ranked number one in mathematics, and possibly the world, though that is arguable these days. Yet, some sports team in Berkeley came up with a big news. In education, we are told that you should always encourage people. When people do good things, students do good things, you give them praise, you give positive reinforcement. But if they make mistakes, don't beat them up, or even psychologically or physically, don't beat them up, right? No negative feedback. Just appreciate the positive, and if they ask you where it was wrong, just point out you made a mistake, but next time try to do better. I'm sure you'll do better, right? And years of psychology and data shows, and educational psychology data shows that it works. So the sports team apparently, and so I'm told actually, came to the conclusion that that is all nonsense and we have just proved it. How? Apparently, to the sports team, they shouted every time somebody would make a mistake, the coach would go and completely rain down on that fellow, right? And make the fellow feel miserable. And then they gave statistics and they found that the next day the fellow did better. So now this seems to disprove all the educational psychology. Maybe this country has gone soft. Right? The reason our education is so terrible, people are not learning anything, is because we are not picking up the stick and beating them up. Because right away, after you scold them, the next day they perform better. Can anyone point out the flaw in the reasoning?
Yeah. The law of averages.
What does that mean?
So even if the person was not corrected, he would still go to their mean and then they...
Wonderful actually. How do you know that even without that scolding, the person would not have done better? So the multiple flaws. See, you cannot establish causation from sequence. just because shouting at the fellow came before the better performance, you cannot therefore conclude that it was the shouting that made the person do better. If you really wanted to do that, what you could have done is, of all the people who did really badly, divide it into two groups, shout at one, don't shout at the other, and then see if the next day they would, which of the two groups did better. And you would find that both did better. Right? The reason is we all have bad days. Some days we wake up tired because we have been, I don't know, watching Netflix till 4 in the morning, right? And we underperform in our work. Or maybe we have the flu, or for a variety of reasons, we're feeling depressed. Our performances vary from day to day, and some days we have a really bad day. Inevitably, in our performance distribution, that's the low end. It's very likely that the next day we'll do better, shouting or not. And therefore, it fails that test. You didn't do you had no control group, a group of people who did badly, but you didn't shout at. Isn't it? So that is unfortunately, the flaw of sequentiality is so common. Believe it or not, both of these groups, the illustrations that I said, they went on to write a paper about it, or an article about it, about their findings, because they thought it was a sensational finding that went against the grain of common wisdom. It didn't actually. So that is the flaw of sequentiality. The other fallacy that people fall for is called correlation versus causation. We are all taught in school that correlation and causation are different. But what is correlation? I want to quantify that today for you. Correlation has a simple meaning. Let us say that we'll first go to the word covariance. What is this? So take some data. Suppose the data is like this, X and Y. This is situation A. Let's take a situation B. The data is like this. The data is like this. B. And imagine a situation C where data is like this. Now look at A. If you increase X, does Y increase or decrease? Increases, isn't it? And if you decrease X, does Y also decrease? It does, right? So they co-vary, isn't it? Variation is together. You increase X, Y increases. This is positive, you call it positive covariance. One variable change usually has a corresponding other variable change. On the other hand, if you look at B, if you increase X, does Y increase or decrease? If you increase X, you go from, let's say, this point to this point. You're increasing X from, let me call this P to Q. But is Y increasing or decreasing? Decreasing, right? Decreasing. So it is, there is a sort of a contravariance. They vary opposites. You increase one and the other decreases. You decrease one and the other increases. Isn't it, guys? Right? So if I may coin a word, it may be contravariance, or more strictly, it is called negative covariance. It's a negative covariance, right? What about C? When X increases, does Y increase or decrease? There is no relationship at all. For every X increasing, you can find so many points of Y. Let's take this point. Let me call this P. Now, if you go from P to Q, to another point Q, let's say at this point in this zone, are most of the points above the previous value of y or below the previous value of y? There are as many points that have increased as many points that have decreased, isn't it? So there's no real relationship. The points are all over the place. There is no relationship. So no covariance. So that is the concept of covariance. Now the question is, how do you measure covariance? This is geometrically obvious, but how do you do that? The first thing you do is you go and sit in the center of gravity of the data. Just go sit in the center of the data. So where is the center of the data? You go to a new coordinate system that is at the center of the data. So you would agree that the center of the data is here. In this case, the center of the data is here. In this case, the center of the data is here. Right? So you create a new coordinate system, let me call it, you go and set at another, let me call this axis x prime and y prime. It is the axis, the coordinate system, which you get if you sit straight in the center of gravity of the data. Right? Likewise here, x prime, y prime. Now you realize that any point, let's just say this point, its x prime coordinates is nothing but, so this is the x mean, mu of x. It will be nothing but x minus mu of x, the mean of x, because ultimately what is this distance? It is mu of x, isn't it? Likewise, what is this distance? Is the average y values, mu of y, isn't it? So y prime coordinate of any point therefore would be y minus mu of y, right? Now observe something interesting. When you sit in that coordinate system, let's look at picture A. From that perspective, what I will do is now show it in the x prime, y prime perspective. Then you should see that your data, this data now looks like this. Does it look like this? A viewed from the x prime, y prime coordinate system would look like this. You say that this is a positive covariance. What can you tell about this point? You observe that when you look from the center of gravity of the data, most of the points are in the first to third, fourth. They are in the first and the third quadrant, isn't it? And for B, where there is a negative correlation, x prime, y prime, in this system, you would agree that your points look like this. When you are sitting in the center of gravity of the B data, your data will look like this to you, y prime. Isn't it, guys? And most data are now in the second and the fourth quadrant. Are we making sense, guys? Is that correct? Isn't it? So now you do one thing. You observe, I need some way to just, in a way, if I could just somehow count the number of points in the quadrants, that could be a pretty good way of telling whether it is positive or negative. Right? So observe one thing, that in the first quadrant, x prime times y prime is greater than 0. Likewise, in the third quadrant, x prime times y prime is less than 0, because both the x prime and y prime values in the third quadrant are negative, isn't it? But in this, x prime times y prime is less than 0, x prime times y prime is less than 0. Guys, is this obvious? This is very elementary algebra, right? We're having fun with numbers. We are saying, hey, we observe something interesting. In the first and the third quadrant, first quadrant, both x prime, y prime are positive. Third quadrant, both x prime, y prime are negative. So the product is positive. Oops, sorry. This is, I apologize. This is positive, right? And so what can I do? I could take an expression, I average out. Right? What I could do is I could average out quite literally x prime, y prime. First, add up all of the values for all the points. Let's say each point we are giving a subscript I. Sum them up. By the way, this is the same as 1 over n. And you take the first point y1 plus x2 y2. That is what it is. Right? You average out the product. If the products are all positive, then it's positive covariance. If the product is negative, it's negative covariance, isn't it? And so this becomes a pretty good expression for covariance, right? And that is why now you're almost looking at the expression that is quite literally therefore 1 over n x minus mu of x, y minus mu of y. Right? So that is called covariance. But there is one extra thing you can do. What people say is that the data is spread all over the place. What if we could scale it by its standard deviation? Right? So what people sometimes do is there's a quantity called z value. Z of x would be x minus the mu of x over the standard deviation of x. You may be familiar with it from your school, and I'm just reminding you about it. Z value of y, what are you doing? You're scaling it. Why do you scale it? It becomes dimensionless. So for example, if you're weighing the elephant in grams, it's not a good idea to weigh the elephant in grams, right? The data will be really have a big spread, right? On the other hand, if you're weighing the elephant in tons, it will have a pretty narrow variation in the data. So it is hostage to the dimension, the unit you use. But if you divide it by the standard deviation, you realize that it becomes dimensionless, right? Numerator and the denominator dimension goes back. And so when you see the distribution of the z value, it's called normalization. Then in the normalized distribution, you'll see the weight of the elephant look pretty nice. Right? It won't get spread out because, for example, if you're looking at the weight of the elephant in grams, it would look like this. If you look at the weight of the elephant in tons, it would look like this. Now, which of the two is a reality that you want to prefer? Which are the reality that you want to prefer? You say, no, this is hostage to the unit. You can make it dimensionless by doing so-called a standardization or normalization. Likewise, y minus mu of y divided by. So when you do this and you do the covariance of the normalized, so covariance of the normalized values gx, zy, which is any two variable, it has a name. Can somebody guess what this is called? It goes by a very word that everybody is familiar with. It is called correlation. This is the definition of correlation. It's basically covariance of the normalized values. Are we together, guys? Right? That's it. Correlation. So correlation, whenever you make between two variables, it will always look something like this, right? X and Y. Let's say, so this is positive correlation. And then negative correlation is the converse of this. They're going the other way around. That is correlation. So now comes an interesting thought. Looking at this graph, can we say that if X increases, Y increases? Therefore, X is the cause of Y. Y, increase in X causes increase in Y. Can we say that? And that is where there's a flaw in reasoning. You can actually not say that because you can make this plot with Y and X. You can invert the axis. Right? So let me make it very real. Let's say that you have children and you notice that this is age weight. And you notice that when you look at the correlation, obviously of the normalized values, it seems to show normalized z of weight and z of x. It seems to show a distribution like this. Therefore, can you say that aging causes you to gain weight? For children, it might be true, but actually, aging does not cause you to gain weight directly. There are other factors involved. As you age, your body cells divide, they mature, blah, blah, blah. You become taller. Because this graph, if you plot it the other way around, you plotted it as weight, right? And age, you would still see the same relationship. Now you can start asking, oh, I see a positive correlation between age and weight. Therefore, the easiest way to age is to increase in weight. That sounds absurd, isn't it? Right? So, for example, if you start eating, let's say 6 eggs a day instead of 1, and you put on some weight, doesn't mean that you are aging faster than your peers. Right? That is an absurd. So, therefore, the statement that correlation is not causation. We have all been taught this correlation is not, and I will put the word not necessarily driven by causation. People abbreviate it to the phrase correlation is not causation, but I'll modify it with the word not necessarily driven by causation. So, for example, you could argue that as people age, it does lead to weight gain in a very colloquial way, though the scientific point of view would be, well, sort of. What happens is cell division keeps taking place. Your bones become bigger, your muscles become bigger as you age, till you reach your full youth. Till then, of course, you're increasing in both age and weight. So it's the biological process that underlies it. Sometimes it may be causation. For example, if you notice that you study, and the more hours you study, the better you do in the exam, or the better knowledge you have accumulated. Therefore, it would be fair to say that the more studying caused you to acquire more knowledge. The correlation was there, but that correlation does come from a causation, isn't it? Right? You open a tap and you put a bucket underneath that tap, and as time passes, the bucket fills up. So you can say the amount of water in the bucket is correlated to the elapse of time. Again, elapse of time didn't cause the bucket to get filled, but correlation is there. That's a case where time's elapse did not cause the bucket to fill. The cause was something latent, namely the tap was open. The faucet was open, isn't it? So when there is correlation, there are the following situation. X may cause B, cause Y. Y may cause X. You don't know which way the correlation goes, the causation goes, or there is a latent variable that caused both of them to happen. Right? So, for example, on a hot summer day, temperature rises and more children show up on the beach. But you don't say that temperature rose, more children showed up on the beach, more ice cream got sold, let us say, that it is the ice cream selling that caused temperature. Right? It is likely the other way around. On a hot day, rising temperature will cause or influence children to come to the beach and therefore more ice creams to be sold. Right? So sometimes you can look through the dynamic and figure out the causal chain. But correlation in itself does not tell you what it is. So I'll give you a puzzle that, so the world is, if you ever, so on our course portal, by the way, I didn't mention about the course portal. If you go to SupportVectors.io, you all have access to the course portal. The lectures will all be posted on the course portal. You all can self-register to the course portal, and I'll show you the course portal in the end. There'll also be a little quiz for you to review your knowledge on a daily basis. And there are also lots of resources. So the internet is filled with spurious correlations. Funny things happen all the time. It is what is called a spurious correlation. Just an accident, pure accident. That correlation doesn't mean anything at all. Right? So the internet is filled with amazingly weird correlations that people have discovered that just don't make any sense. You shouldn't read into it. But then there are sometimes situations, more complicated situations. There is a latent variable that's causing both a correlation to happen, right? So here's a story that I'll tell you. The population of India, a country in Asia, has been growing since 1945, 1947. It so turns out that the population of donkeys in China for the longest time was also growing. So there's a strong correlation. Now, can you read any relationship causal, like did donkeys in China, like for example, are those donkeys in China taking hints from Indian couples? That would be an absurd, or vice versa, that would be absurd. Nevertheless, you can ask, is this a spurious correlation or is there a latent explanation? I would like to venture a latent explanation. See, both India and China were under the British colonial rule. Now, despite the claims by the British Empire and the Brits that they were a force for the good, they brought civilization and prosperity to the colonies. The truth is otherwise. When these countries both became free, more or less at the same time, 1945, 1947, they were impoverished. They were lands of beggars. The statistics is very depressing. In the post-colonial years, before these countries found their footing, literally tens of millions of people died of starvation. These countries were in such a terrible state. All these colonies, whether in Africa, in Asia, etc., the governments, with all their defects, have done an amazing job of uplifting the population out of poverty, of making food available. They've really gone to task feeding their population. Now, when food is available, it's a Malthus law of population. When resources are there, when food is there, population increases. People don't die of starvation. People tend to have children that survive. Therefore, in both of these countries, populations rose. Population not just of human beings, but of animals, cows, donkeys, goats, everything rose. And therefore, there's an underlying cause of correlation, which was the fact that these both countries became free of colonial tyranny and exploitation. And therefore, they got a chance to finally rise up. And they have all been doing an admirable job of rising up. So sometimes when you see a correlation, you don't just dismiss it, but you can ask, is there a latent cause? Is there a latent factor that is causing this correlation to happen? And then correlation gets even more complex. Sometimes it can be circular, right? A can cause B, B can cause A. So correlation and its relationship to causation is a very complicated topic. And so obviously the right statement would be correlation is not necessarily driven by causation, but certainly worth investigating. Certainly worth investigating before dismissing it as spurious. Sometimes it's obvious, like for example, the number of research papers in a field in a scientific field has nothing to do with number of penguins that are jumping off some island. You can dismiss it logically, but sometimes it's not so clear and you need to think a little bit more about correlation and causation. So I would like to end today with a story. It's really actually true. In the United States, there used to be, and I know that there are people from different countries in the audience, so I'll mention a little bit of a United States history. There used to be these tobacco plantations, and the people who owned those plantations, they were called the Big Tobacco. They're still there, Big Tobacco Company, and they exercise quite a bit of clout. It hasn't gone away. They can still manage to put cigarette advertisements in schools or argue that cigarettes don't cause. So at one time, it wasn't known that cigarettes cause cancer or can be related to cancer. But gradually, evidence, or not evidence, scientists began to observe a correlation. The more you smoke, the more likely you are to have cancer. Right? There was a correlation. Populations that smoke more had greater incidence of cancer. So they started raising the alarm, and they say, hey, um, cigarette is carcinogenic, right? And we should ban cigarettes and so on and so forth. And the tobacco companies were alarmed. Big Tobacco was alarmed, and they said, no, that's not okay. And people started taking Big Tobacco to court for cancer. And as the scientific data mounted, it became hard to deny the correlation. So then the tobacco companies, they needed a good way out. What do? They thought, okay, we are going to lose in court now. So let's bring in the big gun. So who was the big gun? All the data was being used. A statistic, it was all statistics, isn't it? So they got the great luminary of statistics, right? His name is Fisher. I believe Ronald Fisher from England, flew him in, right? Who was himself absolutely fond of smoking and pro tobacco. They called him in and he went to the court. And so I heard the story. He said, of course, there is a correlation between smoking and cancer. And everybody is stunned. Oh, Big Tobacco just accepted that, right? But then he argued cleverly that it is not that smoking causes cancer, but it is cancer that causes smoking, right? So the way the story goes, he argued, and apparently successfully, to claim that if you have cancer, you don't know it, you're suffering. And because your body is suffering, it craves cigarette. And cigarette is a great palliative, right? And so the Big Tobacco is doing humanity a tremendously philanthropic thing by making cigarettes available, right? And so if you look back at it, hindsight, there was a reason that case that Big Tobacco should have won in hindsight, despite the cruelty of it all. Correlation is not a winnable argument because it can always be inverted. Right? What emerged after those years is people painstakingly, carefully worked out the biochemical pathways of how tobacco, how nicotine, in very precise causal ways, does damage to the biochemistry of the human body and leads to cancer directly. And that evidence came after a few more years of research. And then, of course, today, only crackpots would argue that smoking or nicotine doesn't cause cancer. So that is descriptive statistics. I would like to stop at descriptive statistics today. It is the part of machine learning or data science that is perhaps the most useful, but that people sort of treat as flyover territory. They are all eager to jump into algorithms. And in the next 3-4 days, we will focus on algorithms. And I'll also do something practical. Today was a general introduction. We will talk about supervised learning, clustering, classification and regression, unsupervised learning, that's pattern recognition, clustering and dimensionality reduction, and we'll talk about reinforcement learning. So we'll cover a lot of interesting territory. But I thank you for coming to this session today. I hope you had as much fun listening to it, or almost as much fun as I had talking about this wonderful topic and sharing it with you.